inviting me and giving me the opportunity to talk about my work. My name is Mathilde, and today I'm going to talk about the temporal and spatial length scales in oxygen-18 observations. I'm actually going to mostly talk about spatial length scales because that's what I worked on. And then I will give a very short introduction of the work of Xavier Davila, who worked on the temporal length scales of the ocean oxygen observations. So first of all, I thought it would be interesting to give a quick introduction of my journey in the world of science so far. I've started in 2019 in France by doing a marine engineering master, which actually gave me quite a few opportunities of internships. I went to Malta and to Gran Canaria for 3 and 2 month long internship. And I also went to the University of Bergen for an Erasmus exchange in fall 2022. I actually then decided to stay in Bergen, Norway to write my master thesis and in spring 2023. So I wrote my master thesis with the Norwegian Research Center. I was working for the Ocean Ice Project with Ellen McDonough, and I was part of the work package 5. And that is the work I did then that I'm going to talk about today. After that, I decided that I wanted to have a broader and more thorough teaching and learning into physical oceanography. So I've decided to start a physical oceanography master still in Bergen in Norway. I'm still carrying this master and I'm writing another master thesis with Elin Darelius, and I'm now writing about basal melting beneath the Fimbul ice shelf. And finally, I'll be graduated in June 2025, and hopefully I will keep on with probably a PhD. Now on to the subject of the oxygen isotopes. Those isotopes are very interesting and important because they give a window on the past, the present, and also maybe the future climate and the circulation in the ocean. More specifically, what is interesting is the ratio of oxygen-18 and oxygen-16 isotopes, because they are comparable to salinity and they help identifying the freshwater sources in the ocean. As I said, I was working for the Ocean Ice Project, whose main goal is to understand the outcomes of the melting of the Antarctica and its consequences on the Southern Ocean and the entire globe. More specifically, this project focuses on the emergence of deep water masses and their impacts on global circulation. I was part of the work package 5, and my job was to build a code to, at any point in the ocean, calculate the decorrelation index, which I'm going to talk more in the later slides. And I was working with the temperature, the salinity, and the oxygen isotopes. I was also working at the surface of the ocean, but future work will expand my work to the whole water column. So let's give one more slides about the isotopes and why they are interesting. As I said, I was interested in the ratio oxygen-18, oxygen-16. The only difference between those two oxygen isotopes is that the oxygen-18 is heavier because it has 2 more neutrons than the oxygen-16. So basically, when I can use my mouth here, when clouds are going to form and at mid and low latitude, they're going to be a bit richer in oxygen-16, since the oxygen-16 is lighter, so it's going to evaporate easier than the oxygen-18. And then those clouds are going to journey towards the pole, and along the journey, they're going to condense and precipitate above the ocean. However, oxygen 18, which is still present in those clouds, is heavier and is then going to precipitate easier than the oxygen 16. So we're going to have precipitation above the ocean, rather enriched in oxygen 18. And when the clouds are going to reach the pole, they are basically going to be depleted in oxygen 18, because oxygen 18 will have mostly precipitate above the ocean earlier on in the journey. So the snow in the interior of Antarctica or Arctic, but today we're mostly talking about Antarctica, has 5% less oxygen 18 than the ocean water. And when this snow or ice is going to melt, we're going to have a signature in the ocean, because we're going to have a difference between the ocean water that is rich in oxygen 18 compared to the ice water that is rather rich in oxygen 16. And that's why it's important. Now on to the data that I've used. So the decorrelation length scales were calculated from state estimate fields of certain properties from a method that is called the total matrix intercomparison method. This method set up a self-consistent relationship between the global mean circulation and the traces distribution throughout the seasons. So going from the raw data from the hydrographic program of the World Ocean Circulation Experiments, it builds up this relationship while regarding the boundary condition and the mass flux, and the outcome would be a matrix of 2 degrees by 2 degrees all over the ocean at any point along the water column. And that is this 2 degrees by 2 degrees resolution matrix that I've been using for my analysis. As I said earlier on, I'm just focusing on the surface of the ocean, but this matrix gives information about the traces all along the water column. Now on to the method that I've used. So I've used this rather simply, if I can say so, autocorrelation function. The autocorrelation function measures the correlation of spatial series with a lagged version of itself over successive space intervals. So it helps to identify the degree of similarities between the observations as a function of the space lag between them. This function can, for example, help to identify seasonal variability or trends in any kind of data. But what I've been interested in is not the correlation, but is the decorrelation. So the decorrelation length scales indicate the lag at which spatial changes in a property stop being correlated. So it means that I am interested in the point where there is no more similarity with the original spatial series. And that decorrelation point happens when the autocorrelation value is worth 0, as you can see on the first figure. And so what I call a decorrelation length scale is the lag at which this autocorrelation value is worth 0. So that's basically what I've been interested in, and I understand that it might still be very blurry, but we're going to keep diving into it, and this will hopefully become clearer afterwards. So now on to some preliminary results. If you look at the right-hand side figure, you can see different lines of different colors. So this is an analysis of, it's a zonal decorrelation length scale analysis of the sea surface oxygen isotopes in the Arctic Ocean. And as you can see here, for example, if I consider the red line, it shows the decorrelation length scale taking the whole globe into account. So from 1 degree east to 400 degrees east. The green one would be the same, but with 20-degree lag. So from 19 degree east to 400 degree east. The blue line is a second lag, so 39 degree east to 400 degree east, on and on and on. And we can see that the decorrelation length scale decreases while the size of the spatial series decreases. So we have a decorrelation length scale that varies proportionally to the size of the spatial series. However, if you look here on the left-hand side, you can see that for the red and the green line, which are the two largest spatial series, we have this very large decorrelation length scale at approximately 81 degrees north. And that is interesting because it put on the table the idea that the decorrelation length scale can identify different water masses depending on the size of the spatial series. So as I started introducing it, I found out that there is a dependence between the decorrelation length scales calculated from the autocorrelation and the length of the spatial series. In general, the shorter the spatial series, the shorter the decorrelation length scale, and thus the smaller the structure that is represented. However, as you can see here, this relationship breaks at some given length scales for a few iterations where the length of the spatial series is increased, but the decorrelation length scales stay relatively constant. So we're going to have this staircase-like feature that you can see on this figure here. So from this staircase, we can infer three different categories, which are kind of representative of the size of the sample structure. So we're going to have a first small scale, rather eddy scale, of approximately 250 kilometers wide. Then we're going to have an intermediate scale that is rather approximately 600 kilometers wide. And then finally the gyre scale, which is 1,000+ kilometers wide. We can also identify water masses on this figure. This figure shows the decorrelation length scale, the zonal decorrelation length scale of the sea surface oxygen isotopes ratio in the Southern Ocean. So each point represent the decorrelation length scale at each grid of this 2 by 2 degrees matrix I've explained to you earlier on, all over the Southern Ocean. So, as I've been explaining earlier, we can identify different length scales depending on how wide the spatial series that we consider is. So at small spatial series of a few degrees, as you can see at the very bottom of this figure. So when I say a few degrees, that would be a few hundreds of kilometers. The decorrelation length scales are about 250 kilometers. And at this length scales, the structures are categorized as mesoscale eddies. For longer spatial series, so if you look at the second, from the bottom, second block, so 50 to 100 degrees wide spatial series, the decorrelation length scales typically increases to 500 to 1,500 to 2,000 kilometers. And there we can feature the presence of small gyres. At even larger spatial series, the identified features correspond to large-scale gyres. And then above that, we can identify larger currents, but this is not really of interest in my analysis. So I've been mostly interested to those first three smallest, if I can say so, length scale. So once again, the spatial frequency of the sampling highly depends on the size of the water mass feature that is intended to be observed. Once again, if we want to observe mesoscale eddy, we're going to consider a rather small spatial series, while if the point is to identify larger features such as large gyres, we're going to use rather large spatial series of thousands of kilometers wide. Now on to some more concrete results. So the point was to produce 3 types of maps. Why 3? Because as I said earlier, there's approximately 3 length scales that I've been interested in. The small, the medium, so the small, which is eddies, the intermediate one, and the large gyres. And I've built up an algorithm that detect automatically those features. So here on the screen, you have a map of the Southern Ocean, and you have a map of the small scale features. This is a westward decorrelation length scales for the surface temperature, salinity, and oxygen isotopes. One thing that we can notice is the pervasiveness of eddies in the Southern Ocean. Because as I explained earlier, the small scale is the eddy scale. And this agrees well with our knowledge of these structures in the Southern Ocean. Although here the length scales identified are an order of magnitude larger than what has been previously suggested. This is the westward analysis, but the eastward analysis that I haven't shown gives the same results. Now up to the medium scales. Once again, the larger the length scale, the larger the water mass structures identified. Here, once again, I'm showing a westward decorrelation length scale analysis for the surface temperature, salinity, and oxygen isotopes in the Southern Ocean. And what we can mostly see here is that the westward length scales are coherent with the meridional flow of the Antarctic Circumpolar Current, where decorrelation length scales reach up to approximately 1,400 kilometers wide. Once again, here only the westward analysis is shown, but I haven't shown the eastward, but it gives the same type of result with the signature of the meridional flow of the Antarctic Circumpolar Current. Finally, on to the large scales. What can be identified here is the Ross and the Weddell gyre as structures of temperature, salinity, and the oxygen isotope ratio. What can be observed here is that decorrelation length scales are greater in the Ross gyre than in the Weddell gyre. But in general, the similarities among the decorrelation length scales highlight the tight relationship between the oxygen isotopes and the salinity. As you can see on these 3 maps, we have very high similarities between salinity and oxygen isotopes, while the temperature map is a bit different because temperature is typically correlated on longer length scales for both the Ross and the Weddell gyre. Now on to a short summary of this work. So the main outcome of my work has been that we can, with the decorrelation length scale, depending on the length of the original segment that is being analyzed, we can identify multiple length scales, up to 3. The smallest would be the eddy length scales, typically 100 to 300 kilometers wide. The intermediate length scale from approximately 500 to 700 kilometers wide, and finally the gyre or the gyre scale from 1,000 to 1,500 kilometers wide. The results have shown or have actually comforted what one already know about the pervasiveness of eddies in the Southern Ocean. That's for the smallest length scale. For the longer length scales, it has been depicted once again the zonal nature of the Antarctic Circumpolar Current, along with the structure of the Ross and Weddell gyres. One thing that can also be mentioned is that from this work, we understand that the decorrelation length scales is anisotropic. So if we look at meridional length scales, it will mostly feature the circumpolar current, while the northward scales indicate, for example, the northward spreading of the Subantarctic Mode Water from the Weddell and the Ross gyre. Yeah, so I wanted to thank you very much once again for inviting me to talk about my work, and I will be very happy to answer any questions or talk later about this. Thank you very much.